Now we will continue our discussion on the properties of vectors. So last time we talked about how to add vectors. We talked about head-to-tail method, commutative and associative properties, and also we distinguished vectors and scalars, and we also talked about equality of vectors. Now, when we say we have the negative of a vector, so that's if you have vector A and minus vector A, that means that these two vectors will have the same magnitude, but they point in opposite directions. So if this is our vector A, minus A vector has exactly the same magnitude, but points in the opposite direction. So when we add vector A with vector minus A, we should get 0. Subtraction. Now, vector A minus vector B is actually equivalent to saying we're adding vector A with a negative of vector B, so minus B vector. So here is our vector A, here is our vector B. So if you look at minus B, it's going to be the same magnitude pointing in the opposite direction. Now with head-to-tail method, we're going to add these vectors. So A minus B becomes this vector A minus B. Well, there's an alternative method. So if you plot these vectors such that they originate from the same point, so this is vector A, this is vector B, the vector A minus B points from vector the tip of vector B to the tip of vector A. So that's an alternative method to figure out what vector A minus vector B is. So it's a vector that points from the tip of vector B to tip of vector A. Alternative method is this. So now we can talk about multiplication by a scalar. If we have a number m that is positive, if we write ma, this is going to be a vector that points in the same direction as a and has the magnitude m times magnitude of a. For example, if this is vector a, this is going to be vector 2a, twice the magnitude pointing in the same direction. A minus ma vector is again a vector that points in the opposite direction of a but has the magnitude m times the magnitude of vector a. Now, in doing algebra with vectors, it's quite often convenient to work with components of vectors. So the components of a vector are found by looking at the projections of a vector onto coordinate axes. So if this is vector A, we look at its projection onto the x-axis and call the projection AX, and projection onto the y-axis called the projection AY. A vector that points from the origin to the point AY is the AY vector, and that points from origin to point AX is the AX vector. So we can write this A vector as the sum of AX vector plus AY vector. So if with head-to-tail method we connect these, we see that we're going to get the vector A. So vector A has magnitude A, AX vector has magnitude AX, AY vector has magnitude AY. Now how do we find these components? Well, this is a right triangle here. So we can see that if you look at the cosine of the angle theta, it will be AX divided by A. If you look at sine of the angle theta, it will be AY divided by A. So looking at this right triangle, we can figure out that AX is A cosine theta, AY is A sine theta, or the magnitude A will be square root of AX squared plus AY squared, because this right triangle we have Pythagorean theorem, AX squared plus AY squared will give us A squared. And we can find the angle theta that this vector makes with respect to the x-axis by looking at the tangent of the angle in terms of the components. So tangent theta is AY over AX, or theta is tangent inverse AY over AX. Now we have 4 possibilities for these vectors. If vector A is in the first quadrant, then AX and AY components will be positive. if you have a vector b in the second quadrant, you see that the x component, projection onto the x-axis, will be negative, but the projection onto y-axis will be positive. A third quadrant, we have a vector c. Its projection onto x-axis is negative and y-axis is negative. So cx and cy are negative. Or if you have a vector in the fourth quadrant, vector d, then you see that it has a positive x component but a negative y component. Okay. Now, what is a unit vector? A unit vector is a dimensionless vector with magnitude 1. For example, for x, y, and z axes here, we can define these unit vectors I hat, j hat, and k hat. These vectors have magnitude 1, they're dimensionless, and they point in plus x, plus y, and plus z directions respectively. So the magnitudes are 1, and with these unit vectors I hat and j hat, we can see that this ax vector, the projection of the a vector onto the x-axis, is ax, the magnitude multiplied by the unit vector I hat. A y vector is ay magnitude multiplied by the unit vector j hat. So we can write the a vector as the x component ax I hat plus the y component ay j hat. You can see that from this equation also I hat is ax vector divided by its magnitude, j hat is ay vector divided by its magnitude ay, therefore its dimensions. Okay, so if we're going to do addition of vectors using projections, a vector plus b vector, since these vectors can be written in terms of the unit vectors and the projections onto the x and y axes here, a vector is ax I hat plus ay j hat, b vector is bx I hat plus by j hat. If we add them up, we get ax plus bx I hat plus ay plus by j hat. So the resultant vector is has a component rx on the x-axis, it's rx I hat, and as a component ry on the y-axis, it's ry j hat. So these components are ax plus bx and ay plus by, as you can see from the algebra here. So as a result, we can also write the magnitude of the resultant vector as square root of rx square plus ry square, which is square root of ax plus bx parentheses square plus ay plus by parentheses square. And the angle this vector is going to make with respect to the x-axis is again found by looking at tangent inverse of ry over rx, which is ay plus by divided by ax plus bx. Now, if we generalize this to 3 dimensions, we have the 3 unit vectors I hat, j hat, and k hat. So any vector A can be written as ax I hat plus ay j hat plus az k hat in 3 dimensions. So let's look at an example. The vector A has a magnitude 5, vector B has a magnitude 5. If you add these two vectors, you get 6 j hat. What is the angle between these two vectors, a and b? And a and b are vectors on the xy plane. So if I write a plus b, I get ax plus bx I hat plus ay plus by j hat, that is 6 j hat. So looking at the two sides, for the I hat part, I have 0 here, so ax plus bx is 0. For the j hat part, I have ay plus by equals to 6, and they have the same magnitude 5. So if I plot these on the x and y xy plane, you can see that the vector A has magnitude 5 and it's pointing in this direction, and vector B has to have exactly the same magnitude 5, and because ax is going to be equal to minus bx, it's going to have the same, the projection of b vector onto the x-axis will have the same magnitude. So this distance is the same. So you can see that I have an isosceles triangle here. Two sides are the same. So because the sum of the y components has to be 6, by dropping this perpendicular here, I can see that this is going to be 3, this is going to be 3. Therefore, this is a 3, 4, 5 triangle. Now, what is the angle between these two vectors? The angle is theta. So if I call this angle alpha, because I have an isosceles triangle here, this angle also has to be alpha. And because this line is parallel to the x-axis, this angle is also going to be alpha. So 2 alpha plus theta will be equal to 180 degrees. Therefore, the angle that I'm looking for is 180 degrees minus 2 alpha. And looking at this right triangle here, tangent of alpha is 3 divided by 4. So alpha is tangent inverse of 3 over 4, which is roughly 37 degrees, 36.87 degrees. And theta is 180 minus 2 alpha, which is 106.26 degrees. So that's the angle between the two vectors. Now we can define two types of products of two vectors. One is called the dot or scalar product. The other one is called the cross product. Now in the dot product of two vectors, vector A and vector B, the dot product is going to give us a scalar quantity which is found by looking at magnitude of A, magnitude of B multiplied with cosine of the angle between them. So if you take the dot product axi hat plus ayj hat, dot product with bxi hat plus byj hat, so writing these vectors in terms of their components, because I hat dot I hat will be equal to 1, because cosine 0 is 1, and I hat dot j hat will be equal to 0, because cosine 90 is 0. But cosine 0 is 1. So we can see that this dot product will give us ax bx. For the first one, I hat dot I hat. Ax by I hat dot j hat is 0. Ay bx I hat dot j hat is 0. And then we will have ay by because j hat dot j hat is 1. So it's also, in terms of the components, the dot product is given as ax bx plus ay by in 3 dimensions, in 2 dimensions. In 3 dimensions, there will be a plus az bz here. Okay, so cosine of the angle between the two vectors is then the dot product ax bx plus ay by divided by the product of the magnitudes a, b. So if you go back to the previous example, this example, we can write ax plus bx squared, parentheses squared, that is ax squared plus 2ax bx plus bx squared, and ax plus bx was equal to 0, so this is going to be 0. Ay plus by parentheses squared is ay squared plus 2ay by plus by squared. That will be square of 6, 36. So if we add them up, we get ax squared plus ay squared plus 2 ax bx plus ay by plus bx squared plus by squared. Since the magnitude a is square root of ax squared plus ay squared, this will be a squared. Then I have in parentheses twice the dot product between two vectors, and then I have magnitude of b squared. So magnitude of a and magnitude of b were equal, they were 5, so this is 25 plus 25 plus twice the dot product of a and b is 36. So I can see that the dot product between a and b is minus 7. This is magnitude of a, magnitude of b, cosine of the angle between them. So cosine theta is minus 7 divided by 25, and the angle is 106.26 degrees, as we have found by looking at this graphically. Now, the second possibility is the cross product of two vectors. So this product gives us not a scalar quantity by a vector, but a vector quantity. So a cross b is a resultant vector r, whose magnitude is given by the magnitude of a multiplied by magnitude of b multiplied by sine of the angle between them instead of cosine. So instead of cosine, we have the sine of the angle. And this vector r is perpendicular to both a and b, and its direction is found by right-hand rule. So if this is vector a, this is vector b, you point in the direction of vector a, curl your fingers, right-hand fingers, towards vector b. Your thumb points in the direction of the resultant vector r. Now, in terms of components, if we look at I hat, j hat, and k hat unit vectors here, and if we go in the counterclockwise, if we go in the clockwise direction, not counterclockwise, it's going to be positive. So this is going to be I hat cross j hat will be k hat, j hat cross I hat will be minus k hat. So if we go in the clockwise direction, we will have a positive. If we go in the counterclockwise direction, we will have a negative answer. So counterclockwise will be negative. So I hat cross j hat is k hat. Why? Because magnitude of I hat multiplied with magnitude of j hat, 1, 1, gives us 1. Sine of the angle between them, sine 90 gives us 1. So it's going to be another vector with magnitude 1. So it will be a unit vector. And if you look at the right-hand rule, for I hat, so j hat and k hat, your right hand points in the direction of I hat, curl your fingers towards j hat, the thumb points in the direction of k hat. So this is also found by using these cyclic permutations here. So you can immediately see from this arrangement that k hat cross I hat should be j hat. Now, if we're going to take the cross product of two vectors whose components are given, we can use the determinant. So basically, A cross B is the determinant of I hat, j hat, k hat, ax, ay, az, bx, by, bz. Now, to take this determinant, first we have a plus, then minus, plus, if we're taking it with respect to the first row. So for the I hat component, which is plus, we have aybz minus byaz. Aybz minus azby times I hat. For the j hat component, so we're going to get rid of this row and this column, then we will have axbz azbx, axbz minus azbx, but because of the minus sign here, it's a minus j hat. And for the k hat component, we have axby minus aybx multiplied with plus k hat. So this is how we can calculate the cross product in terms of the components. Now, there are some important properties of the cross product. If you look at A cross B, it is actually minus B cross A, which you can see immediately with using your right hand. Basically, by changing the order of the vectors in the cross product, we change the sign of the resultant vector. If two vectors are parallel, because sine 0 is 0, their cross product will be 0. If they are perpendicular to each other, the magnitude of A cross B will be AB, because sine 90 is 1. So that is going to give us a 1. And if we take the cross product, A cross parentheses B plus C, there's a distributive property of cross product over addition, A cross B vector added to A cross C vector. So let's quickly look at an example. A rectangular parallel pipe has dimensions A, B, and C as shown in figure. So it has dimensions A, B, and C. Obtain a vector expression for the first diagonal vector R1. What is the magnitude of R1? And notice that R1 ck hat, R1 ck hat, and R2 make a right triangle. So R1 ck hat and R2 make a right triangle. Obtain a vector expression for the body diagonal vector R2. So this is our rectangular parallel pipe. So you can see I have the unit vectors I hat, j hat, and k hat here. R1 vector is the face diagonal, so its projection onto the x-axis is A, onto the y-axis is B. Therefore, R1 vector is AI hat plus BJ hat. What is its magnitude? It is square root of Rx squared plus Ry squared. So R1x squared plus R2y squared, R1y squared. So this will be a square root of A squared plus B squared. And if I look at R1 vector and ck hat vector, you can see that R1 vector plus ck hat vector gives me R2 vector. So R2 vector is AI hat plus BJ hat plus ck hat. So it's basically the body diagonal. You could also see this by looking at the projections onto the x, y, and z axis. The projection onto xy plane is basically the r1 vector. The projection onto the z axis is c. So this basically gives us ai hat plus bj hat plus ck hat as the answer. So to summarize, we've looked at some properties of vectors. Negative of a vector, we take the opposite direction, the same magnitude. Subtraction, we go from the tip of the second vector to the tip of the first vector. Multiplication by a scalar, we just look at the direction. If it's positive scalar, then it's going to be m times a vector in the same direction. If it's negative, then we have to change the direction. It will be in the opposite direction. We can take the components of vectors onto x, y, and z axes, and those components are found by using these right triangles here. X component is magnitude multiplied by cosine, y component is magnitude multiplied by sine, and the magnitude and the angle with respect to the x-axis can be given in terms of the components ax and ay as square root ax squared plus ay squared and tangent inverse ay over ax. We talked about 4 quadrants, 1, 2, 3, 4, and we see the sign change of these components depending on which quadrant we're in. We talked about a unit vector, which is a dimensionless vector with magnitude 1. For x, y, and z axis, we have I hat, j hat, and k hat unit vectors. And the vectors can be written in terms of unit vectors using their components. For 2 dimensions, a vector A is ax I hat plus ay j hat. And you can see that these unit vectors have magnitude 1 because they're equal to a vector quantity divided by its magnitude, so the dimension disappears and the magnitude becomes 1. And addition can be done in terms of the projections here. And also, we talked about an example where we have the 2 magnitudes of the vectors a and b are equal, and their sum is 6j hat. First, we have done a graphical solution to find the angle between these 2 vectors, considering the relationship between their components. And then we have defined the dot product, which is a product between 2 vectors that gives us a scalar, and it's found by multiplying magnitude of 2 vectors and cosine of the angle between them. And it can also be calculated in terms of the components as ax bx plus ay by plus az bz for 3 dimensions. And using the dot product, I have shown you that we could also solve the same problem, and we can see that ax plus bx parentheses squared plus ay plus by parentheses square is a squared plus b squared plus twice the dot product between a and b. We can also obtain a vector out of the product of 2 vectors. That's using the cross product. Its magnitude is ab sine theta, sine of the angle between them. The direction of the resultant vector is found by using the right hand rule. We point our right hand in the direction of the first vector, curl our 4 fingers towards the second vector, and our thumb points in the direction of the resultant vector. In terms of unit vectors I hat, j hat, and k hat, if we do cyclic permutations in the clockwise direction, that will be plus. In the counterclockwise direction, that will be minus. And with that, we're going to have I hat cross j hat is k hat, j hat cross I hat is minus k hat, and k hat cross I hat is j hat. And if we want to calculate the cross product of 2 vectors using their components, we can take the determinant of I hat, j hat, k hat, ax, ay, az, bx, by, bz. And some properties of the cross product we talked about. A cross b is minus b cross a. If 2 vectors are parallel, their cross product is 0. If they're perpendicular, the magnitude is going to be a times b, and a cross b plus c is a cross b plus a cross c. And we worked on this rectangle parallel pipe to find the direction of the body diagonal vector r2 here. And basically we see that the r2 vector has a projection onto xy axis as r1 vector, which has ai hat plus bj hat. the components are a and b. The magnitude is square root of a square plus b square, and R2 vector is R1 vector plus ck hat, because we have these two vectors added on with the head to tail method gives us R2 vector, and its component on the z-axis is also equal to